Hello guys, this video is related to Unit 7 Biomechanics and Sport and Exercise Science and specifically looks at C3 levers as part of the assignment 7.3, all about angular motion. So you may be familiar with levers from school, from physics or possibly from one of your PE classes. Essentially, having a look at this image on the left-hand side, hopefully you would be able to recognise the components that are part of a lever system. This one happens to be a first-class lever system, and again, you may know from school, there are actually 3 different class lever systems, 3 different organisations of these components. Essentially, we've got within a lever system, we've got a fulcrum, which is basically the pivot point, the axis about which the angular motion rotates. So this is an elbow joint, of course. The joint is often the fulcrum. We've got a load, and in this example, it would be the weight of the forearm and the weight in the hand, whether it's a dumbbell, a shot put, whatever it happens to be. So the combination of those two, the limb itself and the weight being held, is the load, and that's obviously being acted on by gravity heading vertically downwards towards the centre of the earth. Then we've got an effort. So effort is the muscular action that acts about the joint. So we've got triceps brachii. Triceps attaches not, the far side of the elbow joint on the ulna. So the attachment is just to the left of the fulcrum. So the fulcrum happens to be in the middle. The effort is attached on the left and the load is on the right of the fulcrum. There's 2 other factors we've got though. So this marks this actually from an A-level exam question, but this mark scheme incorporates 2 other terms. So we've got our lever, the bones. The long bones act as levers. We know that already. We've got a fulcrum, which is our pivot point, our joint. We've got the load, which is the weight or the resistance that we want to try and move. And we've got the effort, which is the muscular action that causes levers to move about the joint. But if you look at number 5 and number 6, we've got 2 other labels, a load arm and an effort arm. Now, the load arm is essentially the distance, the perpendicular, so the right angle distance between the fulcrum and the load. And you can see in this example, it's 0.3 meters. So the load arm is 0.3 meters. The effort arm in this example is the distance between the fulcrum and the effort. Of course, this is much smaller because the triceps brachii attaches right by the joint. So in this example, the load arm is quite a lot longer and bigger than the effort arm, and there are implications for that. So when we describe load arm or effort arm, it's the perpendicular distance of each aspect, each component from the fulcrum. So those are the basic components of a lever system in general, and this example happens to be a first-class lever. So there's a little summary table similar to the mark scheme, I guess, but just a little bit perhaps clearer for you to have a look at. Each component and the terminology and the objects within a system that relate to that. And it's these lever systems that bring together the musculoskeletal system, the bones and joints that enable our muscles to act on, apply forces on and around to create motion. And we use this all day, every day, especially, of course, within sport and exercise science. Now, I just want to introduce 2 terms that become quite relevant through the rest of this video. Mechanical efficiency. So each type of lever system that we'll look at is kind of designed and organised, those components are organised to be either mechanically efficient or, have mechanical advantage, I should say, or be mechanically disadvantaged. And if they're disadvantaged, it doesn't mean they're rubbish. It just means they're not good at certain things. Now, we need to look at the force generation, the strength a joint system, a lever system can generate, versus the range or speed of motion, what range of motion it has and how quickly it can move through that range of motion. And depending on the organisation of those components within a lever system, lever system will either have mechanical advantage or mechanical disadvantage. So I talked about the effort arm and the load arm, the perpendicular distance from the fulcrum. If the effort arm, so between the muscle and the fulcrum, is bigger, longer than the load arm, the perpendicular distance between the load and the fulcrum. So if the effort arm is bigger than the load arm, we would consider that lever system to be really good for strength, really efficient and advantageous for strength, but not so good for range of movement and speed of movement or motion. The reverse of that, of course, is true. If it's the other way around, if the load arm is bigger than the effort arm, then that particular lever system structure is not so good for strength and is much better for range of movement and speed of movement. And when we look at each lever system and we'll look at some examples, you will see this quite clearly. So the fundamental thing to remember is if the effort arm is bigger than the load arm, there is mechanical advantage, and that lever system is great for strength. And it's the reverse for mechanical advantage. Load arm bigger than the effort arm, good for range of movement and speed of movement. Let's have a look at an example then, just to see if we can apply the components of the lever system. So the takeoff of a long jump or a triple jump. We've got the toe, the ball of the foot acting as the fulcrum. We've got the load of the athlete's body acting downwards just to the left of the fulcrum. And the main muscle group that acts as the effort, of course, is the gastrocnemius, which attaches at the Achilles, at the heel. Obviously, that is contracting concentrically to plant or flex the ankle joint and project this athlete into the air. Now, would you know what lever system this is? And we decide what lever system it is based on the order of these components, where they are in relation to each other. Now, in this example, the load is in the middle between the effort and the fulcrum, which means it's a second class lever. And the second question would be, is this type of lever system mechanically advantageous or disadvantaged? And we know that because it's to do with the effort arm, the effort to the fulcrum, versus the load arm. If the effort arm is bigger, longer, which it is, it's further away from the fulcrum, then we would describe this lever system as having mechanical advantage. It's really good for strength. Your ankle joint is really good for strength. Given this tiny little muscle or two muscles move your body and can make you jump, contribute to you jumping, it's incredibly strong. Okay, let's move forward then. So we're going to work through three types of lever system and just see if we can identify the organisation of each of the components to work out, so that you could work out in any example what type of lever system was involved. So we've got the example of a head. Now I've happened to show a person falling asleep because it shows the muscular action, or in this example, lack of muscular action, that's made this lady's head flop forward. So could you identify the load, the fulcrum and the effort? Hopefully so. The fulcrum is obviously the neck joints that the head pivots, your nodding action happens around. The load is the weight of the head. Your head is incredibly heavy. So in this case, the load is pulling your head down. Gravity is pushing down through the mass of your head, pulling it down to the ground. And what normally would be in place when you've got a normal head upright would be there would be muscular action at the back of your neck, pulling your head to balance it on top of this fulcrum. And that's obviously not happening in this example because this lady has fallen asleep and this muscular effort has stopped and her head has flopped forward as she's sleeping. So this is a slightly better, I guess, diagrammatic version of it. We've got the load on the head, we've got the fulcrum, the neck, we've got the effort, the muscular action at the back of the neck here, these strong muscles at the back of our neck. And obviously if she was awake, those muscles would be contracting to keep her head balanced on this fulcrum. Would you know what classification of lever that is based on the organisation of these components? And of course, let's not forget that the bones act as levers. So the head is an example of a first class lever. Now I've put this up in the top right corner here to help us remember this acronym FLE. First, second, third class lever, FLE. And what that means is this is the component that is in the middle of the other two components. So for a first class lever, F is in the middle. Fulcrum is in the middle between the effort and the load arm. So first class levers, the fulcrum is in the middle, and we've got the effort and the load on either side of that rotational bit. So here's the fulcrum in the middle, got the load arm, the effort arm. Now, does this lever system have mechanical advantage or not? If we look at this example down here, where the distance between the load and the effort is exactly the same, is one dominant? No, which means that if there's equidistance, then it's neither advantage nor disadvantage. It is essentially kind of neutral. It's strong and has good range of movement. But not all of first class levers are equidistant, like this example. For example, here we've got the effort arm with the triceps, the fulcrum, and we've got the long load arm. So this is still a first class lever with the fulcrum in the middle, but in this example, our load arm is longer, which means there is mechanical disadvantage, and this lever system is great for range of movement, speed of movement, but not so great for strength. So if you were doing tricep press, if there was a dumbbell in your hand here and you're doing tricep extensions, that's great for range of movement, but quite hard muscularly. And then this example down here, the sculler, the rower, they've got this sort of bridge here, which is the fulcrum. So their oar rotates around that little cradle that the blade sits in. They've got the load, the water that they're pushing against, and they've got the effort, the pull action on the handle there. So again, it's a first class lever because the fulcrum's in the middle, but because the load arm is longer than the effort arm, this system is good for range of movement, speed of movement. So you can get a big, long stroke, but actually the effort to do that by the rower's body and arm is quite hard work. So first class levers, fulcrum in the middle, depends where the fulcrum is in relation to the effort and the load arm as to if it's mechanically advantaged or not. Next example, different kind of lever system. We've already looked at calf and ankle already. So the fulcrum is the ball, the contact with the ground. The load is the body weight. The effort is the gastrocnemius acting over the ankle to create plantar flexion once you do your calf raise, your heel raise. And again, here's a slightly better diagrammatic version. Load in the middle and the fulcrum and effort either side. Now, because the load's in the middle, we might know that it's a second class lever system. There's some more examples here. Fulcrum, load in the middle, effort either side. Sometimes you see an F, doesn't mean fulcrum, it means force, effort. Here's another example. It's not sporting, but it's just to show you. So please don't use these examples in your work. It's just to identify. We actually have second class levers for an advantage. So carrying the wheelbarrow with a longer effort arm is helpful to us. Turning and undoing a nut is easier because we've got a pushing down with a longer sort of, I don't even know what it was, I can't remember, a wrench is more efficient for us, more advantageous for us than if it was a really short one, because it makes the effort arm longer. So always use sports examples, but this is just to help you understand the principle behind second class levers. So again, second class levers have the load in the middle, FLE, second class lever. Here's the diagram of it. This shows, of course, a fulcrum, the load arm, the effort arm. Now, load's in the middle, the effort arm is longer than the load arm. Hopefully you know where I'm going with that. So load's in the middle, effort and load arm, effort and fulcrum on either side. Because the effort arm is always going to be longer than the load arm. So here, from the fulcrum, the effort arm is always greater than the load arm. Then you should know that this is a mechanically advantageous lever system. There is mechanical advantage because the effort arm's bigger. So this system is great for strength and power and force generation. This tiny little gastrocnemius muscle can contract to create plantar flexion and lift your whole body weight off the ground, which is pretty incredible. It's not so great for range of movement or speed of movement though. It can't have a great range of movement, but it's really good for strength. Okay, so let's look at the final type of lever system, the final classification. So here we've got a bicep curl, an elbow joint, which, as you might know, is going to be the fulcrum. The joints are always the axis points that movement happens around. We've got the load of the forearm and the dumbbell. Remember, it's not just the dumbbell, it's this whole system, the weight of the forearm and the dumbbell. If we remove the dumbbell, the forearm on its own would be the load that gravity is acting down upon to try and push down. And the biceps brachii would be our effort arm. Now, looking at a slightly better anatomical diagram, you'll see that the biceps brachii attaches on the ulna just to the right-hand side of the fulcrum. So the fulcrum's the joint. The effort arm is this short distance here, and then the load arm is this longer distance here. Now, in terms of structure and the organisation of those three components, we've got effort in the middle, and load is always going to be further away from the fulcrum, which gives us clues. Here's some more examples for you. Leg extension. So this one's an interesting one because we may not picture this very clearly on our own body, but this image shows it very nicely. So the knee joint is the fulcrum. The quadricep muscle, so rectus femoris is one of the main quadricep muscles, attaches via the patella tendon. You can see the little patella bone there, and it attaches onto the tibial tuberosity, this lump on the tibia. So fulcrum, effort, because when the quadriceps shortens and pulls, it shortens here, but it pulls on this point here. So the effort is actually applied, the force is applied via this tuberosity to the ulna, which then gets pulled upwards when we do a leg extension. But in order to do a leg extension, we've got to overcome the load of our lower leg. So the lower leg is the load, the effort is this connection here, which is generated by the muscle on our thigh, but it's attached just below our joint. So we've got effort in the middle very clearly. Some other examples are kayaking. So the top hand is the fulcrum. The bottom hand pulls, that's the effort. And then, of course, the blade has to apply against the water, so the load is that way. So you push against the load. Third class lever system. The fulcrum is the hands on a push pass in ice hockey or field hockey. The load is obviously the puck that you've got to push against, and the effort is your muscular action applying a force on the stick in that direction. In all of these examples, then, we've got the effort in the middle, the effort component in the middle. So going back to my acronym, FLE, first class lever, second class lever. When E is in the middle, effort's in the middle, it's a third class lever. So effort's in the middle, load is always furthest away from the fulcrum. So load arm is always the dominant arm. Now this, you can pause the video, this text here implies that actually, although the load arm is always going to be longer than the effort arm, sometimes, in some examples, we can manipulate how different they are. If the effort arm is really short compared to the load arm, then we have quite a significant mechanical disadvantage. But if we can manipulate, let's say, a skill technique to increase the length of the effort arm so it's only just a little bit less than the load arm, then we can generate more force and we won't be as mechanically disadvantaged. Now, this is not true in our body. So our hamstring muscle here attaches just by the fulcrum. We can't change that. We can't say, right, I want my hamstring to attach down by my ankle. So the load arm is only a little bit longer than the force arm. We can't change that. Let me go back to the other diagram actually. We can't change our attachment of our quadricep to say, I want it to attach down by my ankle. So the load arm is only a little bit bigger than the effort arm. If it was like that, then this joint, this lever system would be pretty good at strength and only a little bit disadvantaged. As it is, it's mechanically disadvantaged. It's great for range of movement, but quite weak compared, to that. It's not so great for strength. However, looking at this athlete here, let's say they wanted to generate bigger force. What they could do is move this left hand further down the stick, which gives it a longer effort arm and only a little bit less than the load arm, and therefore they can generate bigger forces. Or this person paddling, can you imagine trying to paddle with the hand really near the fulcrum at the top here? It would be very hard. They'd have to generate a massive force to pull through the water. But because they've got a lower hand, or even if they've brought it a little bit lower, it's less effort to address that force and to compete with that force. So in techniques, we can manipulate how long the effort arm is, but in our body, we can't. So third-class levers with effort in the middle are designed primarily for range of movement and speed of movement, and they're not so great comparatively for strength. So we would describe third-class levers as being mechanically disadvantaged. Interestingly, the majority of the levers in our body, in our limbs, are third-class levers. They are designed for movement and not necessarily as much for strength generation.